Hi there, it's Paul Bamberg with the introductory video for Class 5 of Math 117. You should watch this before you come to class on September 15th. And the topic is the Borel sigma field and measurable functions. These are both concepts that it takes a little while to wrap your head around, but let's see what we can do. Probably the most important thing we'll try to do in this course is calculate the expected value of a random variable. A random variable is a function from the sample space to the real numbers, and a good example of computing the expected value of a random variable involves a dartboard. You throw the dart at the board, it sticks somewhere in the board, and each point on the board has a score value associated with it. And what we need to do to calculate the expected value of a single throw is take all the possible scores. For each of those scores, multiply the score by the probability of its occurring, and then add things up. Now, if you think about this, you'll realize quickly that such a calculation will be impossible if you can't answer the question, did the dart hit in the region where the score is 20? Someone says, I can't really tell you. I can tell you whether the dart hit in the region where the score was either 20, 30, or 40. You say, that's not good enough. So that means that the sigma field is going to have to include certain events if we're going to be able to do this calculation of expectation. Actually, the phenomenon is a bit more general. We'd like to be able to answer a question like, was the score on the previous throw somewhere in between 5 and 30? And a sigma field that only allows us to figure out whether the score was less than 20 or greater than 20 wouldn't be good enough for that. That means that our choice of sigma field is going to restrict the possible scoring functions that we can use, and the choices of scoring functions that are consistent with the sigma field are what we call measurable functions. Here's an equivalent way of looking at the same situation. If we have a measurable scoring function for the dartboard experiment, that imposes a very simple requirement on the sigma field. Namely, if we have an event of the form the dart hits in a region that leads to a certain score, that event has to be in the sigma field. We can talk about this connection without ever mentioning probability functions. And this, in fact, is going to be the last major topic we consider before actually introducing a so-called probability space. I've warned you already that uncountable sample spaces pose problems in that the power set 2 to the omega, where omega is uncountable, is so big that it's not a useful sigma field. However, we can't ignore uncountable sample spaces because R, the set of real numbers, is a perfectly good sample space. The experiment might be, for example, you acquire a certain radioactive nucleus, you watch it until it decays, and the event that occurs is it decays at a certain time. That's a point in the sample space, so the sample space is R. More generally, whenever we have a measurable function, this is a function from the sample space to the real numbers. The real numbers are the codomain. And so the next thing we have to address is what appropriate subset of 2 to the omega, the power set of omega when omega is the real numbers, is an appropriate sigma field. And the name for this sigma field, which was invented in the 20th century, is the Borel sigma field. The events in this sigma field are the so-called Borel sets. In fact, almost anything you can think of is a Borel set. An open interval is a Borel set, so is a closed interval, so is an isolated point, and any countable unions of such sets is also a Borel set. The reason I mentioned Vitali sets, in fact, is that I think a Vitali set is the simplest example of a subset of the real numbers that is not a Borel set. But how do we define the Borel sigma field? The definition is that it's generated by the open intervals. That is, you start with open intervals and then take complements and countable unions until you finally have the entire Borel sigma field. But this focuses attention on the open intervals in a way that's ultimately illusory. Let me point out why. Think about all the open intervals that extend from just less than a minus 1 over n, to just greater than b. If you ask what numbers lie in all those open intervals, well, a does, b does, and so does everything in between a and b. In other words, this infinite intersection is the closed interval that goes from a to b. So you can make a closed interval by taking an infinite intersection of open intervals. If we consider the open intervals that extend from 1 over n below x to 1 over n above x, the only number that lies in all those intervals is the set that contains the single point x. So you can make a set with a single point in it by taking intersections of open intervals. The other way round, you can ask, what's the union of all the closed intervals that extend from just beyond a to just short of b, from a plus 1 over n to b minus 1 over n? Well, neither a nor b lies in any of those intervals, so it's not in the union. But any number ever so slightly greater than a does, so does any number ever so slightly less than b. So this infinite union of closed intervals is in fact an open interval. What's going to turn out to be useful to know, and this is a proof that you'll have to learn for this class, is that if you consider intervals that start at minus infinity and extend up through an arbitrary rational number q, these intervals, and there are only countably many of them, also generate the Borel sigma field. Now let me address the issue of inverse images. We're going to denote random variables by capital letters from near the end of the alphabet. Random variables will typically have names like capital X, capital Y, and capital Z. If we're talking about a point in the domain of one of these random variables, that is a point in the sample space, we'll denote that generically by the Greek letter lowercase omega. In general, the domain is not Rn for any value of n, and omega may be something that doesn't make much mathematical sense. Don't think of omega as being a real number or anything made in a simple way from real numbers. Now for inverse images. We'll consider a function f whose codomain is C. What I mean by the inverse image of that subset of the codomain is the subset of the domain that gets mapped into C. And the best way to think about this is with a dartboard. C might, for example, extend from 5 to 20. The inverse image of C is the collection of regions of the dartboard where the score you get lies in between 5 and 20. In spite of the notation F inverse, there's no implication that the function f in the equation that you just looked at, or the random variable x, is an invertible function. Let's do an example with an ordinary function first. F is the cosine function. If I ask, what's the inverse image of the closed set from 0.5 to 1? Well, there are a bunch of angles near 0 extending from minus 60 degrees to plus 60 degrees, where the cosine of the angle falls in that range. And then there's another region around 2 pi radians, 360 degrees, where that happens, another one around 4 pi radians, and so on. So this inverse image is actually a countably infinite union of intervals. It's not a connected region at all. Now for measurable functions. We have a random variable, x. The domain is the sample space. The codomain is the real numbers. And this is going to generate a sigma field whose members are the inverse images of Borel sets. That's hard to think of in the abstract. Let me give you a specific example. Suppose you've got a dartboard divided into 3 zones, and the scores from these 3 zones are 0, 5, and 10 points, respectively. Then this scoring function generates a sigma field in which a typical event is going to be something like the score is not 0, i.e. the dart hit either in the 5-point zone or the 10-point zone. Or the score is 10, the dart hit in the 10-point zone. If this sigma field that is generated by the random variable x is a subset of the sigma field, which we're calling just plain sigma field f, then we say that x is F-measurable. And what that means is that f subdivides the sample space enough that we can use x as a scoring function. Here's some examples of how you can test whether a function is measurable. If you want to show that a function is not F-measurable, all you have to do is find any Borel set, and a single point is probably the simplest sort of Borel set to use, whose inverse image is not in F. What that means with the dartboard example is if you can find, for example, a possible score value like 5 where the region of the dartboard that leads to a score of 5 is not in the sigma field, then this scoring function is not F-measurable. If you want to show that a random variable is F-measurable, you've got a slightly bigger job on your hands. A good way to proceed is find a simple collection of Borel sets that generate the entire image of x. For example, if the image consists of the values 5, 10, 15, and 20, all you have to do is to show that the inverse image for each of those scores is in the sigma field. That is, that the 5-point region, the 10-point region, the 15-point region, and the 20-point region on your dartboard are all in the sigma field. If the image of the random variable is uncountable, then life is not quite so simple, but what you can do is to ask yourself, what is the region where the score is less than some rational number q? The open set from minus infinity to q is a Borel set, and you want to insist that the inverse image of that set is in the sigma field. And since sets of this form generate the entire Borel sigma field, if each such set is in the sigma field, you are fine. Now let me say a bit about indicator functions. We've got an event A in our sample space. It has an associated indicator function denoted by 1 sub A with a boldface 1. This function has the value 1 for points in the sample space that are in the event or subset A, 0 otherwise. That means that the inverse image of the set containing 1 only is A, the set of values for which the indicator function gives 1, and the inverse image of the set consisting only of 0 is the complement of A. But you can invent the inverse image for an arbitrary Borel set. It just depends on whether or not 0 is included and whether or not 1 is included. If you have a set like the one that includes 0.3 and 0.7 that doesn't have 0 or 1 in it, the inverse image is the empty set because you can never get either of those values. If, on the other hand, you had the Borel set that extended from -1 to +2, then the inverse image of that must include the entire sample space because you always get the value 0 or 1 from an indicator function, and it always lies in that Borel set. The nice thing about indicator functions is that you can use them to re-express fundamental set operations. In particular, the indicator function for the intersection of events A and B is just the product of the indicator functions for A and B. If something lies in the intersection of A and B, both those indicator functions will have the value 1, and so will their product. For unions, life is a little bit trickier. The indicator function for the union of A and B is the sum of the indicator functions for A and B minus their product. Think about it. If something is in both A and B, the indicator function for A gives 1, the indicator function for B gives 1. That's 2, but when we subtract off the product, the result goes back down to 1 and we're correct. And finally, the indicator function for the complement of an event is just 1 minus the indicator function for the event. Turns 1 into 0, turns 0 into 1. This is just a simple example of the general principle that you can make new measurable functions from old measurable functions by adding, subtracting, and multiplying the measurable functions that you already have. So let's think about how we can make F-measurable functions from indicator functions. First, let's consider the simple case of a finite sample space. In that case, the image of these indicator functions is necessarily finite, and the level sets of the form x inverse of some particular value c form a partition of the sample space. You can think, perhaps, of a dartboard with only a finite number of spots that you can hit on it, and then all you have to do is partition into points that give rise to a score of 1, points that give rise to a score of 2, and so on. However, you've got to be a little bit careful. The level sets may form a slightly coarser partition than the partition that generates the sigma field for x. How could this happen? Well, it might be the partition includes 0.1 and 0.2, but the function is the indicator function for the set that includes both 1 and 2. That is a function that has the value 1 on both 1 and 2. In that case, the only event you need is either you hit 0.1 or 0.2. The sigma field doesn't necessarily have to include the event hit 0.1 or hit 0.2 in order for this function to be measurable. Now we've got a nifty way of making sigma fields out of indicator functions. I'm going to use the term simple function to refer to a finite linear combination of indicator functions. You take indicator functions like 1 sub a sub I for various events, multiply them by real numbers c sub I, add them all up. That's certainly a function on the sample space. But now there are only going to be certain values that this x can achieve, because the x is going to be the sum of the constant c sub I for all the cases where the indicator function gives you a value of 1. That's going to partition the sample space into a new partition, b sub j. You can think of this as sort of the total score is 1, the total score is 2, the total score is 3, and so on. And for each of those sets, there's an associated value, which I'll call d sub j. And so you can alternatively represent the function as d sub j, the value, times an indicator function that is constant on b sub j. Think, for example, of rolling 2 dice. The smallest score you can get is a 2, and that will give you 2 times the function that is 1 if you roll a pair of 1s. The next possible value is 3, and that 3 gets multiplied by the indicator function for the set that consists of 1 on the first die, 2 on the second, and 2 on the first die, 1 on the second. Later on in the course, functions that can be either positive or negative are going to give us some difficulties. And our usual way of getting around these difficulties will be to take a random variable x and writing it as a difference of two functions, x plus and x minus. X plus is equal to x whenever x is not negative, otherwise it's 0. X minus is equal to minus x when x is not positive, and 0 otherwise. So these are both positive functions, and you can say that with this definition, the absolute value of x is equal to x plus minus x minus. If this function x is F-measurable, then its positive part, its negative part, and its absolute value are also going to be F-measurable. And I realize, yes, I do have a typo here. The absolute value function of the function x is going to be x plus plus x minus, because x minus is defined to be minus x when x is not positive. X minus is necessarily a positive number. I will fix that in the notes, but I'm not going to redo this whole recording. So let's try to summarize what we've concluded about cases where we've either got a countable partition of the sample space or a countable range for a function f. If you've got a sigma field that's generated by a countable partition, then any function, in order to be measurable, has to be constant on each set in the partition. This is obvious if you think about it briefly. This says that you can't have a function that equals 2 on part of a certain set in the partition and 4 on the other part of that set, because if this is a partition, you can't break it up into smaller pieces where the scores are 2 and 4 respectively. This is nice to know because if the partition's countable, then the level sets must be countable. The random variable x therefore has countable range, which is going to turn out to be a simple case that it's easy for us to deal with. The converse is also true. If x can take on only a countable set of values, you can express it as a linear combination of indicator functions for sets where the value is x sub 1, the value is x sub 2, and so on. These sets are pairwise disjoint. They don't have to form a complete partition because it may be there are parts of the sample space that don't occur in any of the b sub n. If all those b sub n are in your sigma field, then the function is F-measurable. Finally, if you have a function x whose range is countable, then any function, let's call it y, that is measurable using the sigma field f sub x has to be constant on the level sets of x. Let's look at an example of creating a function that's constant on the level sets of x. This function y is a function on the sample space, and I'm going to define it to equal some numerical valued function f applied to random variable x. My only requirement is that the function little f be Borel measurable, but that just means the inverse images of a Borel set has to be another Borel set. That is almost always true. This is a very easy requirement to meet. We're not going to worry about it any further. In that case, y inverse of b, the part of the sample space where y has a certain value, is just the portion of the sample space where f inverse of b leads to a certain value for x. This is obvious with an example, though difficult to see in the abstract. Let's let f be the squaring function, and let's let our Borel set be the set consisting of the single value 4. What's the inverse image of 4 under f? It's the set of numbers whose square is 4. That consists of the two values, -2 and +2. And in this simple example, you can immediately see the level sets of x for -2 and +2, that is, the regions of the dartboard where the score is either -2 or +2, coalesce into a single level set for y, the larger region of the dartboard where the square of the score is equal to 4. With that discussion of level sets, we conclude this introductory topic.